One of the things you're going to have to be able to do, or you should be able to do, or you want to be able to do with simple harmonic motion is to understand the relationship between these following four variables versus time for an object that's moving in simple harmonic motion. Okay, and this is also a great review for our earlier work on motion and even Newton's second law. Okay, so here they are. There's position, where the mass is on an x-axis as it oscillates back and forth. Its velocity as it moves back and forth, its acceleration as it moves back and forth, and the sign and magnitude of the restoring force as it moves back and forth. And in particular, we're interested in relating, or just knowing, first of all, when is x, where x is the, well, really it's the position, but it's also, you could think of it as its distance from the equilibrium position. When it's at a maximum, how does that relate to the velocity? Let me start over. Basically, we want to understand when is x going to be at a min-max, when is velocity going to be at a minimum and maximum, plus and minus, I should say, when is acceleration going to be at a maximum, plus and minus, and when it's zero, and when is the restoring force going to be plus and minus maximum, and when it's zero, and how do these relate to each other and to time? Now, that sounds like a very hard thing to do, but you're going to find that from our earlier work on motion and Newton's second law, you're going to see, and graphing of these, you're going to see that it should all make perfect sense. And the key thing is to start out with the key kind of points in the motion. And I made a big boo-boo. Well, no, I didn't actually. Because what we want to start out is, okay, I did make a boo-boo. Let's look at our oscillator. And what we don't want to think that this line goes to this and this line goes to this. This is just to orient you on the motion. What we're going to do is we're going to have a simple harmonic oscillator. We're going to basically do work, think about adding energy, that comes next, is we're going to do work pulling this thing away from its equilibrium position until it's at a position of A. And guess what A stands for? Amplitude. But right now we can just think of it as point A or position A. Then we're going to let it go, and it's going to oscillate back and forth. And we're going to see that it's basically going to go from A to negative A as it goes back and forth. And that's the motion that we're going to be graphing here. So it's okay that I confused myself. At first I thought these relate, but they don't. This is just the motion, and these are the graphs for that motion. Okay, so what we're going to do is we're going to pull this thing over to position A at t, and then we're going to let it go at t equals 0. So let's think about what's going to happen. Okay, so when we let it go, obviously it's not going to stay at position A because there's going to be a significant restoring force that is going to pull it back to the middle. So we're going to see that it's going to go from A over time. It's going to start here. And then I'll just make little circles just to kind of identify the points of interest. And then we're going to see is that sometime later it's going to be back to the equilibrium. Now, of course, I hope you realize that mass has inertia. And so once this thing gets going and it reaches the equilibrium position where the force is going to be 0, it's not going to stop, right? It's going to have inertia. It's already moving. So it's going to blast right through the equilibrium position. And then the restoring force is going to slow it down, and then it's going to reach a negative A. So sometime later it's going to be at, this is negative A right here. And so we're going to find that at sometime later it's going to be here. And then it's going to go back. So now we have the restoring force here is going to push it back towards the equilibrium. And it's going to arrive there at some point in time, and then you can see it's just going to cycle. So it's going to start at A, move through the equilibrium till it's at negative A, go back through the equilibrium, and return eventually back. So this is one complete cycle, right, once we draw it. And then it's going to go down to the equilibrium again, or return to the equilibrium, and my time is out. Okay, so I'm doing this in pen, so I got to go for it here. Well, let's talk about, it's going to be a cosine curve. But let's talk about what's going to happen here. It's okay, so this thing is going to accelerate rapidly until it reaches some peak value at the equilibrium, and then, okay, I just got to go for it here. No time to talk. I've got to draw, I'm busy drawing a cosine function versus time. And that's not too bad. Oh, no, yes. Okay, yeah, it's going to be not moving. That's right, initially not moving, then accelerating. Okay, that is hopefully that looks like a trig function, like a cosine function. Okay, and that's what the motion is going to be. Now we could go into some detail about, let's come back to the actual slopes of these. Remember what does the slope of a position versus graph tell you? Versus time graph? Yes, that's right. Velocity at any instant. Now let's look at the corresponding velocity versus time graph, and we're going to do that in red. Okay, now without marking up this beautiful graph here, I want to think about the slope, right? Remember, velocity is the slope of your position versus time graph at any instant in time. So this is supposed to be flat here. It's initially not moving at t equals 0, and so our initial velocity is going to be 0. But see what's happening here. The slope of this line is going from 0 to more and more negative, more and more negative, more and more negative, and reaching a peak negative slope right at this interval. And that's negative slope. So we're going to have some peak negative value here. And I guess I should make that V max, minus max, negative velocity max. And let's just go back at our transition points here. Okay, we're back to 0. Does that make sense? We're saying that it's not going to be moving, but where? When it's at a position of negative A. And hopefully that's going to make sense. When it gets back to the other side, an equal distance away from the equilibrium position as the A, it's going to be back to not moving thanks to that restoring force. So what we're going to see here is the slope. Now we're back to 0. Now it's going to be slamming back towards the equilibrium position on the way back. That's what this position is. And we see we're back to maximum slope, but now instead of negative, it's going to be positive. So I guess I got to make a decision here right about there. Positive slope, positive value. And guess where it's going to go? It's going to go back to A. And at this instant in time, it's going to not be moving. And we can see that the slope is, the slope is 0, so this is going to be back down to 0, and you can see this periodic motion. But let's see, okay, now we're back to peak. So we're at a maximum slope, but now, and again, it's negative. Now, where's that happening? At the origin. Okay, and so, let's see, where's that? Right about here. And then again, we go back. Now we're back to negative A, and that's what this thing is doing. It's speeding up as it gets to the, so if we start here, it's speeding up as it gets to the equilibrium position. It's at peak speed. The restoring force at this position and at these various instances in time is 0. So because it's already moving, it's going to keep going peak speed, and then it's going to slow down as the restoring force pushes it back in the other direction. Okay, so we're back to 0 here, and now, yikes. Okay, now I just got to go for it here. So, okay, so we can begin to make some important connections here. Let's see, should I make some notes? We'll try to summarize it later. When your oscillator is at a position of A or negative A, we see that, okay, so that's occurring here, that's occurring here, that's occurring here, and that's occurring here. What is the velocity of your oscillator when it's at the endpoints, or when it's at the peak or maximum displacement from equilibrium? You can see that it's not going to be moving, and hopefully that makes sense. That's when it's basically doing its turnaround, or when it's reversing direction. We also see that we have peak negative velocity and peak positive velocity at these points. And how do they correspond to position? When your oscillator is at the equilibrium. So here we start negative, so fastest at the equilibrium, fastest at the equilibrium, fastest at the equilibrium. And that's hopefully makes sense again, because that's where the oscillator is being pushed back to the equilibrium. The restoring force is reducing, temporarily zero. Then it's growing to come back in the other way. And so your oscillator is always going to be going fastest at the midpoint, slowest at the turnaround points. So if you study these two graphs, so it's a good review. It's a good review of how the slope of the position versus time graph helps you build the velocity graph. And this is what I mean by relating position to velocity, is when is this thing going to be going fastest? When is it going to be going slowest? Okay, now let's build the acceleration graph. Again, a review. This, you know from earlier that the acceleration of an object is defined to be the slope of a velocity versus time graph at an instant in time. So let's start at the beginning here. We see peak negative slope here and here. But let's focus on here. So that's a negative slope, and it's also, and we see that the slope is, the magnitude of the slope is getting less, so we're going to be peak negative. So we're going to start right there. I've committed. That is our peak negative slope. And then what's happening to the slope of the velocity versus time graph? It's approaching zero. Right there, flat. So that is zero. Then we have, okay, so when it gets back to the equilibrium, we have, wait a second, now I could, no, silly me. That's not okay, when we have zero velocity, we don't care the zero, but I mean, that's interesting. It's zero velocity, but we have max positive acceleration here. Let's see. How about there? Okay, I'm confused, and I just confused myself. We don't want to confuse where something is with its velocity, and that's what I just did right there. I made a little mistake. So this is velocity, and this, so okay, so the slope here, max positive slope, max positive acceleration. Zero slope, whoops, zero acceleration. Max negative slope, max negative acceleration. Zero slope, zero acceleration. Max positive slope, max positive. Okay, so now we can begin to trace this out. Oh, shoot. I'm not feeling it on this one. Okay, so now we have a third graph now. Let's see, when is this thing going to be, let's relate the acceleration graph to the velocity graph. Okay, I see that we are at peak, let's just start, okay, let's call this negative A max. So we're at peak negative acceleration when the oscillator is at its peak positive position, at its amplitude, positive amplitude. Let's see, does that make sense? Well, I think so, because when you got this is basically when you got the oscillator stretched out this way, what is the direction of the force going to be? That way or that way? This way. And we know from Newton's second law, if the force is this way, negative, what direction is the acceleration going to be? negative. Okay, so we see that the acceleration is going to be the opposite sign of the position. Okay, now we come along and we see, oh, there's zero acceleration here. When is that going to occur in terms of position? This thing will not be accelerating, only for an instant, but not accelerating when the object is in the equilibrium position. And that's what we've already mentioned, is that when this thing returns back to its equilibrium position, the restoring force is 0 at that instant. So the acceleration will be 0 at that instant. Then we see that we reach a positive peak value for acceleration at this point. When does that occur? When your oscillator is at its negative, when it's at the position of negative, or basically when it's at its negative amplitude position. Oh, really? When it's over here. Okay, now does that make sense? Why do we have positive acceleration there? Well, because the restoring force is going to be largest, and in the positive direction. And you can see the cycle just repeats. But at each point, you should see a correlation between, okay, I see peak negative acceleration. Let's make a prediction. Peak negative acceleration should occur when? Negative A, plus A, or 0. Peak negative acceleration should occur when you're at positive A. Okay, let's see. Yes, it works. Okay, I have negative acceleration. Where's that going to occur in terms of the position of your oscillator? Well, it better be at the equilibrium. And yes, it's at the equilibrium position. Okay, the last one is force. Okay, well, this one's an easy one. Okay, there is a fly. Get away. Okay. All right, so now we're going to go to, well, this one's easy because we know that there is an absolute relationship to the acceleration of an object and the net force. And since our, that's ridiculous, fly, our coefficient of static friction is 0, let's see, maybe we'll see if we can entice the fly to land here and we can attack him. All right, sorry about that. So there's no friction, so the only X force is the restoring force. So what we're going to see with the restoring force is that it's going to be an absolute mirror image. Now, obviously, the amplitudes. This is qualitative, so it's really all about the shape. So we're going to see that when there's a max negative acceleration, maximum negative acceleration, we're going to have maximum negative restoring force. And 0, when there's 0 acceleration, 0 force, peak positive acceleration, peak positive restoring force, 0 acceleration means there's no restoring force at that instant. Here, peak negative acceleration means peak negative force. So it's a 1-to-1 correlation in terms of the shape. Didn't quite match up here. Okay, so we should get the identical. Identical means you're going to be comparing. Let's see. Okay, well, whether it looks the same or not, it's going to be the same shape. Okay, not bad. Okay, that is the relationship between the where an oscillator is, and so this is the where it is, and its velocity, and its acceleration, and the restoring force. And you need to be able to understand how these graphs relate to each other, and perhaps even build this chain of position, velocity, acceleration, and force graphs.